So here we're given that x plus 1 over x equals to 2 times cosine of theta. We have y plus 1 over y equals to 2 times cosine of phi. Then using these, we have to prove the following. So let's begin with whatever we are provided with. First, we will consider x plus 1 over x. This will be equals to 2 times cosine theta. We will transpose 2 cosine theta from the right hand side to the left hand side. So we'll have x minus 2 times cosine of theta plus 1 over x equals to 0. Multiplying throughout by x, we have x squared minus 2 times cosine theta multiplied to x plus 1. Thus equals to 0. Now this gives us a quadratic equation. So if we use the standard formula for obtaining the roots of a quadratic equation, so we will get x equals to 2 times cosine of theta plus or minus square root of 4 cosine squared theta minus 1 whole divided by 2. So this will be equals to, so we have 2 times cosine of theta plus or minus square root of, so we'll take negative 4 as the common factor. So we're negative 4 multiplied to 1 minus cosine squared theta divided by 2. Now negative 4 is actually 4 iota square, because we know that iota square, that value is negative 1. So we have 2 times cosine of theta plus or minus square root of 4 iota squared and 1 minus cosine squared theta, that's an identity, which is equals to sine squared theta whole divided by 2. So this gives us a value of x. So x will be equals to 2 times cosine of theta plus or minus 2i sine theta whole divided by 2. So we can divide by each terms with 2, which will give us cosine of theta plus or minus iota times sine theta. Let's represent this by equation number 1. We are also provided with y. We are given that y plus 1 over y, that's equals to 2 times cosine of phi. So if we take the same approach and solve for y, then y will be equals to cosine of phi plus or minus iota times sine phi. Now what we'll do for simplicity, we'll only consider the positive value of x, that means cosine theta plus iota times sine theta. So let this be x, and y will be equals to cosine of phi plus iota times sine phi. This will be number 2. So now that we have x and y value, let's go to our first proof. So here we have to show that x, y, z, and this goes on, added to 1 plus x, y, z, and goes on to n number of terms, or it could be infinity. So we have to show that that gives us 2 times cosine of theta plus phi plus rest of the angles. So we'll start with first multiplying x with y. That means we have cosine of theta added to I sine theta, and this whole thing is multiplied to cosine of phi, so this is positive, cosine of phi plus iota times sine phi. This we have already obtained. Now when we take when we distribute cosine theta plus I sine theta with this cosine phi plus I sine phi, we'll have cosine of theta times cosine of phi plus iota squared sine theta times sine phi plus iota times, we have cosine theta times sine phi plus iota times sine theta times cos phi. So this will be equals to, so we have cosine theta plus times cosine phi. So iota squared, this is negative 1. So we have sine theta times sine phi. Plus we'll take iota common. So we'll have cosine theta plus sine phi added to sine theta plus cos phi. So this is the expansion of cosine of theta plus phi plus iota times, and this particular expression is the expansion of sine theta plus phi. This would mean that if we, and this is the product of x and y, we have cos of theta plus phi plus iota times sine theta plus phi. Now let's say we take z to be equals to cosine of, we'll take some other angle, let's say alpha plus iota times sine beta. And when we multiply x, y, and z together, then we will get cosine of theta plus phi plus alpha plus iota times sine of theta plus phi plus alpha. So now if we want to generalize this, that means x, y, and this goes on, this will be equals to cosine of theta plus phi plus rest of the angles added to iota times sine of theta plus phi plus rest of the angles. Next, we are going to use the De Moivre's theorem. The De Moivre's theorem states that whenever we have cosine of theta plus iota times sine of theta raised to the power of n, that this becomes equals to cosine of n theta plus iota times sine of n theta. Now in our case, we have to show that 1 over xyz, so we'll start with 1 over xy to keep things simple. We have 1 over xy, so this is equivalent to xy raised to the power of -1, and we have already obtained the value of x times y. This is the value, which is cosine of theta plus phi added to iota times sine theta plus phi. Now this entire thing is raised to the power of -1. So here our n value is -1. So when we use the De Moivre's theorem, so we have cosine of negative of theta plus phi plus iota times sine of negative of theta plus phi. Now cosine, this is an even function, so we'll simply have cosine of theta plus 5. And since sine is an odd function, we'll have negative iota times sine of theta plus phi. So let me state here, I use the fact here that cosine of negative theta will be positive cosine theta because cosine is an even function, and sine of negative theta, but that will be equals to negative sine theta because our sine is an odd function. So we use this particular fact here and here. Fine. So that would mean that if we have 1 over x, y, and rest of the angles, this will be simply equals to cosine theta plus phi plus rest of the angles minus iota times sine theta plus phi plus the rest of the angles. So here we have obtained, so let me label this as number 3, and this is going to be number 4. Now we will add 3 and 4 together, and we will see that the imaginary part will cancel out and we will be left with only the real part. So that means our final proof will be that we'll have xy multiplied to rest of the terms, and this is added to 1 over xy, and this goes on. This will give us 2 times cosine of theta plus phi plus the rest of the angles. So we've successfully proved the first part. Now let's move on to the next part. So here we have x over y added to y over x, and we need to show that this is equivalent to 2 times cosine of theta minus phi. So we've already obtained the value of x and y. So let's begin with this. So we'll start from the left hand side, but before that, let's try to find out the value of 1 over y. The 1 over y is actually y raised to the power of -1, which is simply cosine of, this is positive, cosine of phi plus iota times sine phi whole raised to the power of -1. If we use the De Moivre's theorem, we will simply have cosine of -phi plus iota times sine of -phi. So use the fact that cosine is an even function, so we have cosine phi, and sine is a odd function, so we have negative iota times sine phi. So this is y raised to the power of -1, and similarly we have x equals to cosine theta plus I sine theta. So that means x inverse will be equals to cosine theta minus iota times sine theta. Now we'll use this. So let's start from the left hand side. So here we have x over y plus y over x. So that will be equals to x times y raised to the power of -1 plus y times x raised to the power of -1, which means we'll multiply x. So our x value is cosine of theta plus iota times sine theta. This will get multiplied to y inverse, which is cosine of phi minus iota times sine phi added to y. So y is cosine of phi plus iota times sine phi multiplied to x inverse, which is cosine of theta minus iota times sine theta. Fine. So let's now simplify this. So we have cosine of theta multiplied to cosine of phi, and we have iota times sine theta multiplied to negative iota times sine theta. This will give us negative iota squared sine theta times sine phi. Now we know that iota squared, this value is equals to -1, so we have positive sine theta multiplied to sine phi. This gives us positive sine theta times sine phi. This will be now added to, so we'll take cosine theta multiplied to iota times negative sine phi. We have Let's start with iota times sine theta. So we have positive iota. This will get multiplied to sine theta times cosine phi minus cosine theta times sine phi. Similarly, we are going to multiply these two expressions. So we have positive cosine phi times cosine theta. Then we have positive times negative. So we have negative iota square, which will still make it positive. So we have sine theta times sine phi. Next, we have negative iota. If we take negative iota as the common factor, so we have sine theta times cosine phi minus cosine theta times sine phi. Right. Now clearly this entire expression and this one gets cancelled out. So here this is the expansion of cosine of theta minus phi, and this also is the expansion of theta minus phi, but that's repeating twice. So this will be 2 times cosine of theta minus phi. So we've successfully shown that this is equals to the right hand side. Now let's move on to the third part. So let's begin. So first we will compute the value of x raised to the power of m. So this will be equals to cosine of theta plus iota times sine theta raised to the power of m. So we can straight away use the de Moivre's theorem to get cosine of m theta plus iota times sine of m theta. So we have obtained x raised to the power of m. So x raised to the power of negative m will be simply equals to cosine of m theta minus iota times sine of m theta. Right. Next we go and obtain the value of y raised to the power of n. And this will be equals to cosine of n phi plus iota times sine of n phi. That means y raised to the power of negative n, that will be equals to cosine of n phi minus iota times sine of n phi. Right. Now let's start from the left hand side. All we have to do is consider x raised to the power of n, which is cosine of m theta plus iota times sine m theta. So this will get multiplied to, again, y raised to the power of n. So this will be cosine of n phi plus iota times sine of n phi added to x raised to the power of negative m. So here we have cosine of m theta minus iota times sine of m theta. So this will get multiplied to y raised to the power of negative n. That means we have cosine of n phi minus iota times sine n phi. Fine. So this will be equals to, so we will multiply cosine of m theta with cosine of n phi. So we have cosine of m theta times cosine of n phi. This will be, now we'll have I times sine of m theta multiplied to I times sine of n phi. We'll have I squared, so this will be negative sine m theta times sine of n phi. And then we will take positive iota as the common factor. So this will get multiplied to, so we have sine m theta multiplied to cosine n phi. This will be added to cosine m theta multiplied to sine of n phi. Next, we have the cosine of m theta multiplied to cosine of n phi. So we have cosine of m theta multiplied to cosine of n phi. That we have negative iota and negative iota, which makes it positive iota squared, but we have negative 1 multiplied to sine m theta times sine n phi. Then we will take negative iota as the common factor. So we will have sine of m theta times cosine of n phi added to cosine of m theta multiplied to sine of n phi. Now clearly we see that the second term and the fourth term cancels out, and we have a first term and the third term that are exactly the same. So that means we will be equals to 2 times cosine of m theta times cosine of n phi minus sine of m theta times sine of n phi. This is the expansion of cosine of m theta plus n phi. So this is equals to the right hand side. So we have successfully shown that this expression is equals to 2 times cosine of m theta plus n phi. Now let's move on to the fourth and the final problem. So we're going to use the results that we have already obtained in the previous part. Let's use it. We'll start from the left hand side. So here we have x raised to the power of m. So this is cosine of m theta added to iota times sine of m theta. This will get multiplied to y raised to the power of negative n. So we have here cosine of n phi minus iota times sine of n phi. Then this will be added to x raised to the power of negative m. So here we have cosine of m theta plus iota negative iota times sine m theta. So this will be multiplied to y raised to the power of positive n. So that's simply cosine of n phi plus iota times sine n phi. Fine, this will be equals to, so we'll multiply cosine of m theta with cosine of n phi. So we have cosine of m theta times cosine of n phi. Then we multiply iota times sine m theta with negative iota times sine n theta. So this will give us sine of m theta multiplied to sine of n phi. Now we have positive iota multiplied to negative iota. So that's simply positive iota multiplied to negative iota. That simply gives us negative iota squared. And negative iota squared has a value of negative 1. So this is simply positive 1. That means we'll have positive sine m theta times sine of n phi. So now this will be added to iota times. So here we will multiply sine m theta. So we have sine of m theta. This will be multiplied to cosine of n phi. We are going to take iota as the common factor. And for the next term we have negative. So here this iota times sine n phi gets multiplied to cosine of m theta. So we'll have negative cosine of m theta multiplied to sine of n phi. Next, we'll multiply this expression, which should give us cosine of m theta times cosine of n phi plus sine of m theta times sine of n phi minus iota times sine of m theta times cosine of n phi minus cosine of m times theta multiplied to sine of n phi. Now clearly the second term and the fourth term goes away, and the first term and the third term, they're exactly the same. So this will be equals to, we'll have 2 times cosine of m theta times cosine of n phi. This will be added to sine of m theta times sine of n phi. Now this is the expansion of expression 2 times cosine of m theta minus n phi. And we have successfully shown that this is equals to the left hand side. 2 times cosine of m theta minus n